from PUC in Peru, who is going to talk about effective integrability of Lins-Neto's family of foliations.
Well, good afternoon with everyone. I would like to thank the organizer for giving me the opportunity to be here. This is a work joined with Luis Gustavo Méndez, and this talk is related to the Poincaré problem, and we recall this problem, like said Posada. Well, Poincaré asked if it is possible to decide if a polynomial differential equation has a first integral, rational first integrals. That means it's all the leaves are algebraic. For instance, if we give this example, we can find easily the explicit form of the first integral because we have this particular equality. Sorry. The Poincaré's strategy to solve this problem was to find a bound of the degree of the invariant curves of the foliation associated to this differential equation in terms of the degree of the foliation. Well, there are examples that we can find this bound. For example, I present you this family given by Alcides Lins-Neto, and this family has all the foliation has degree 4. We can easily prove that if we take the line infinite, it's not invariant, and it has 2 points with the tangency is 2. Also, Lins-Neto proves that the set of parameters where the foliation has a first integral is formed by parameters of this form, Pu plus Q tau, and infinity. Tau is the cubic root of the unity. And also, he proves this degree can be chosen very large, so we can find this bound. Also, Poincaré was interested to find explicitly the integral first integral of this of a foliation. So it was the motivation of our work. For this, I will give you some properties of this family. For example, the tangency set of this family is formed by a Nye invariant line, and this Nye line intersects in these 12 points. Okay, so we have that all the foliation at least have 12 singularities. And also, if we can decompose these 12 points in 4 sets of 3 points, with each set characterized uniquely the foliation which had 3 degenerate singularities. This is because if we have, or if we take a parameter alpha not equal to 1, tau, tau squared, and infinity, these 12 points are radial, that means are not degenerated. But if we take alpha equal to 1, tau, tau squared, and infinity, we have the, we have 9 of them unradials, and the remaining 3, it could be degenerate singularity. So we can characterize this for foliation with these 3 configuration of points. This could be very important for the works. for this work. Now, I present you some nice observation given by Lins-Neto. He characterized that when a foliation of degree 4 it's element of the family. If this foliation leaves invariant the tangency set, we give that, or we have that element. It's this foliation is an element of the pencil. For this observation, we can find explicitly the first integral. For example, if we want to calculate the first integral for f1, no? And it's important to know that the first example that I give you, it's the first integral for the element f infinity. If we take these linear automorphisms of P2, it's easy to prove that it leaves invariant the tangency set. And also, if we take the pullback of f infinity, has degree 4. So, by this observation, we have this foliation is element of the pencil. But we have also that this automorphism leaves P31 to P3 point. So, this foliation must to be f1. So, we can calculate the first interval of f1 taking this composition of this first interval of f infinite and this linear automorphism. Analogously, we can have this first integral for f tau and f tau squared. Now, what happened with the other parameters? Well, we have partial answers given by Lins-Neto again. He proves that the first integral of f pu plus q tau is given by polynomial given by 3 lines of the tangency set and rational curves. But to define this rational curve is not easy. How to calculate these rational curves? We can use other birational transformation. In this case, we use birational transformation of degree 2. Now, we can take the set P3 infinity, and we can give the, we can obtain this standard Cremona transformation, whose point base is these 3 points. Okay, and we can prove that this application takes or leaves invariant the tangency set. Okay, now if we take the strict, if we take the foliation f infinity that we know that it has first integral, we can take this strict transformed by this Cremona transformation, and we obtain a foliation that it has a first integral also. But if we want to know what is the degree of the foliation, we can use this remark. And because for the foliation f infinity, these singular points are non-dicritical, and we can find this is 2, no? Because local is given by xy by x minus y. So we have the degree of h is 4, and by the observation what we observed before, this can be an element of the pencil. Now, it's important to observe that we can do the same for the other elements of the pencil, because these singularities are radial. In this case, also, this vanishes order is 2. Pardon, excuse me. So if we take alpha, we have this foliation F alpha, and we take all the strictest form. We can also have the degree of this foliation is 4. So we can define an application, a bijective application, lowercase q to P1 into P1, and this is an holomorphic map because if alpha is linear in alpha, and the Cremona transformation, it's a composition of a blow up and a blow down. So this application is a Mobius map, but how to calculate this map? Well, we can calculate how this application leaves this configuration of 3 points. Okay, for this, we have Q leaves P31 to P31, so we have Q leaves the foliation F1 to P of F1. So we have that lowercase q1 is equal to 1. Similarly, using this information, we have that q tau is tau squared, and q tau squared is equal to tau. So we can calculate this lowercase q to its 1 over alpha. We can do the same for the other set of points, P31, P3 tau, and P3 tau squared, and we obtain this Cremona transformation, and also we obtain this application. And the importance of this application is because if we start with a foliation with first integral, and we apply one of these applications, we have that we obtain another foliation that it also has a first integral. And also we obtain this composition. Okay. Now, if we want to calculate some first integral explicitly, I am going to draw a lattice formed by 1 and tau, which satisfy this. So we have we can obtain 9 points. Which satisfies this. But we can obtain these 9 points because we remember that we know that F1, F tau, and F tau squared has first integral, but we know tau squared is -1 minus tau. So we have determined F1, F tau, and F -1 minus tau. Now, if we know that F infinity also has a first integral, if we apply in this, we have that 0 is also has first integral, if 0 has first integral. And also, if we apply 0 in this other function, we have -1 minus tau squared. So we have -1 minus tau. In minus tau squared is 1 plus tau. And we complete this other point if we apply 0 for this. If we apply 0 here, we obtain -1 plus tau, and this is here. And in the other equality, we have 1 minus tau. So we can obtain all the explicit form for this foliation, for the respective foliation associated to this point, and I will show you what is the form explicit of this Nye foliation. Okay, but what happened with the other foliation? In this case, if I take Fm plus n tau, we can do this. I am going to express these parameters that order pair. And if we applied this order pair of this of this function, we obtain these new points, but we have now the Euclidean norm of these new points also decrease. Okay, and so if we start with a foliation m plus 1 tau, we can decide which of these three okay, which of these we can decide, because we obtain always we can obtain the parameters have norm, the respective norm, Euclidean norm, less. Okay, and so we can end up with an of any other Nye foliation what we obtained before. So finally, we obtain the theorem of this work that says if we can obtain the expression of the first integral of f alpha m plus n tau, we can start with the foliation of infinity, and then if we apply a finite number of applications of these four applications, we obtain the explicit form of f alpha. So this is all. Thank you very much.